This is Professor Keen, and today I'll be talking about Book 3 of Newton's Principia. I'll be focusing on Phenomenon 3. In the previous lecture, I talked about Phenomena 1 and 2, wherein Newton described the motion of Jupiter's and Saturn's moons around Jupiter and Saturn, and how they obey Kepler's third law of planetary motion. In this third phenomena, which I've put at the top of the screen, Newton is talking about the motion of the primary planets, Mercury, Venus, Mars, Jupiter, and Saturn. And this might sound obvious to us, but I'll read it anyway. He says that the 5 primary planets, Mercury, Venus, Mars, Jupiter, and Saturn, with their several orbits, encompass or go around the Sun. This is something that we take for granted at this point. But a couple of things I'd like to point out. First of all, notice that there are just 5 primary planets. He doesn't mention Uranus, Neptune, and Pluto. You might ask yourself why that is. Well, this is 1687, or if this is the third publication, the early 1700s, and those planets were not known about. So these were considered the 5 known planets. Notice also that he doesn't include Earth here, because he's trying to argue that Earth, like these other planets, are going around the Sun. Newton, of course, is arguing from a heliocentric viewpoint. But recall that this is really not obvious, either to scientists or to the everyday observer. So the question is, how do we really know that it is true? After all, the ancients knew that the Earth was at the center. We know that the Sun is at the center. Why do we believe that? Keep in mind that if you were not indoctrinated since you were a small child into thinking that the Sun was at the center of the universe, you probably wouldn't really believe that. So if you believe that, it's for a reason, and it's either because your teacher told it to you, or it's because you have reasons for believing it. So what are the reasons for believing that the Sun is at the center of the solar system? Well, what Newton is doing here is he's going to provide some of the evidence. The first piece of evidence that he gives is the observations of Mercury and Venus. So evidence for heliocentrism, and specifically that these planets go around the Sun. First of all, I'll use the symbols for Mercury and Venus. That's a symbol for Mercury and Venus. He says these have moon-like appearances. What does he mean when he says they have moon-like appearances? Well, they have phases. Just like our moon has new, crescent, half, gibbous, and full phases, so too do Mercury and Venus have these phases. This is going to be related to his second point, and that is that when they are full, that is when there's a full Venus or a full Mercury, when they are full, they are above. They are above, or we might say beyond the Sun. I'll explain what I mean by this in a moment. I'll just write it down first. And secondly, when they are half, when they're in a half phase, they are to the sides of the Sun, one side or the other, to the side of the Sun. And third, when they are crescent, the crescent phase, or new for that matter, or the new phase. I'll remind you of what these mean in a moment. They are below the Sun. That is closer to us than the Sun. Okay? And furthermore, finally, and sometimes they appear to cross. They appear in front of the Sun. This is something that was observed by some ancient Islamic observers who claim to have seen Mercury and Venus actually go in front of the Sun. Okay? So before I make more comments about this, let me remind you what the phases of the moon are. For some of you, this might be old school stuff. You might already know this, but for some of you, it might be a nice reminder. So remember, when we look at the moon in the sky, there are some times when it is going to be completely dark. Okay, we won't be able to see it. We call this a new moon. And by the way, this is, if you are interested in the Roman calendar, this is where we get the word calendar from the Roman word calends, which is the day on which the new moon appears. The next phase of the moon is when most of it is dark. We call this a waxing crescent moon. The next phase of the moon is when it is half illuminated. Of course, it grows gradually from crescent to half moon. This more technically is called the first quarter moon, or the half moon. And according to the Roman calendar, this was the day of nones. So they had on their calendar, when there was a half moon, they called that the nones of a particular month. And by the way, if we wanted to think about what day these occur on, this would be the first day of the Roman month. And then on the day of nones, that's about the 7th or 8th day of the month. After that comes the waxing gibbous phase. Waxing gibbous, that's a fun word to say, gibbous. Okay. And then after that comes you probably know it as a full moon. Technically, it is called the second quarter because you see 2 quarters of the moon. The other 2 quarters are behind the moon. You can't see those. This is called the full moon. And this, by the way, is called the Ides, according to the Roman calendar. So when Shakespeare and Julius Caesar says, beware the Ides of March, he's meaning beware the day of the full moon of March. That's the 15th day of the month. Then the next phase, I'll draw this over here. We've got this half of the moon starting to be dark. That is the waning crescent moon. After that, we have again half of it that is in shadow. That is the third quarter. That's also what we would call a half moon, but technically it's a third quarter. Finally, not finally, but the next phase, we have the waning. Oops, I did that the wrong way. Let me go back. The waning gibbous. So this is all dark here. Waning gibbous phase. And finally, we have when the entire moon is dark, that would be, again, the new moon, and this would be on the 29.5th day, about 29.5 days, almost 30 days. So that's where we get our month, is roughly speaking the amount of time it takes to go through all phases of the moon. Now, we are all pretty familiar with this with the moon, but you might not be familiar with the fact that the planets, such as Mercury and Venus, exhibit moon-like appearances. That is, they exhibit phases. If you look at them through a telescope, certain parts of them will be illuminated and certain parts of them will not be. Now, notice that Newton is using this as an argument that these planets go around the sun. If you don't think about this very carefully, you might think, oh yeah, well that's a good argument. They must go around the sun. But keep in mind that our moon exhibits phases, and yet our moon goes around the Earth. So why doesn't Newton say because they exhibit phases, they must be orbiting the Earth? In fact, why isn't Earth at the center of the solar system, right? Because if they exhibit phases and the moon exhibits phases, we know the moon goes around the Earth. Why doesn't he claim that Mercury and Venus go around the Earth? Well, it's because of his second point. He's relating the phase to their apparent size. So there's an important correlation that he's pointing out here. So let me draw another diagram that will help illustrate what he's talking about. Okay, so let's draw the Earth right here. the traditional symbol for the Earth is a circle with a little cross on it, because that is where Jesus came. He came to the Earth. So that's the traditional symbol for the Earth. Now, the symbol for the sun is like this, so I'm going to draw the sun like that. And the argument is that Mercury and Venus and so on go around the sun. So let's suppose the Earth is here, the sun is here, and let's take for granted for the moment that Venus is going around the sun. So I'm going to draw Venus at a few different locations. Okay, so let's suppose it's here. That, by the way, again, is a symbol for Venus, and another symbol for Venus over here. So I'm drawing it at 3 different locations with respect to the sun as it's orbiting the sun. Now, let me draw also not only Venus, but what part of it is illuminated. Remember, the sun, of course, is a source of light. So it is going to illuminate the portion of Venus that is facing the sun, right? So I'm going to draw an illuminated side of Venus like this, and then the darkened side of Venus like this. Okay, so I'm highlighting the fact that the sun is illuminating Venus at various locations, and I'll just leave it at that. Okay, now what's the point that Newton is making? He is saying that when we see Venus, so here is you standing on the Earth, if you look up and you see Venus, at some times it is closer to us, and in some times it is farther from us. When it is closer to us, the size of Venus appears bigger. This is a discernible effect you can see when you look at Venus through a telescope. Sometimes it looks bigger. When it's farther away, it looks smaller. And what Newton is saying here is that the size of Venus, whether it's small or whether it's big, is correlated with the phase of Venus. In particular, when you look up and you see Venus looking big, it's also a time when the phase of Venus is new. That is, it appears dark to you. Or at best, you see a little bit of light peeking out on the edge, a crescent Venus. So when Venus, for example, is crescent or new, they are below the sun. That is closer to us than the sun. So if you think of the sun as being high or away, Venus is below the sun. It's close to us, it looks large. On the other hand, when you look up at the times when you see Venus and it appears small because it is far away, those are the times that Venus appears to be in the full phase, because the sun is illuminating the part that we can see. That's what he's saying here. When Venus, is full, they are above or beyond the sun. So if you think of the sun as being kind of high away from us, Venus is beyond it, far away. And finally, the point is that if you look up and you see Venus at the same distance away as the sun, we can argue about how we know how far away it is, but when it's between its closest and its farthest distance, that is when it appears half to us. So we will see half of it illuminated. And that's precisely the point that he's making here. So what he's doing here is giving us evidence based on the correlation of the phases of Venus with its size, that it would be reasonable to assume that Venus itself is going around the sun. Okay, now keep in mind that the fact that Venus is going around the sun does not imply that we are going around the sun. It could be still the fact that the Earth is sitting still, the sun is going around us, and Venus and Mercury, for that matter, are going around the sun. So this in and of itself is not proof that the Earth is one of the planets going around the sun. Okay, so it's a good thing to keep in mind. I go through these arguments in a lot more detail in my Physics 101 class, so I'm just kind of sketching out some of the points that Newton raises here in order to argue for the fact that the Earth is a planet going around the sun. Okay, what's another piece of evidence? So we're talking about evidence for heliocentrism. A third piece of evidence, he says, is that Mars and Jupiter and Saturn, those 3 planets that were known at the time, their phases are likewise correlated with their sizes. I don't want to spend a lot of time going through his arguments, but I want to sketch out what kind of things he's talking about. So these are the kinds of arguments that Newton gives to just let you know that he's on board with the idea that the Earth is one of the planets that are going around the sun. Mercury is going around the sun, Venus is going around the sun, Mars, Jupiter, and Saturn are all going around the sun. Okay? Let me just set up for the next phenomenon. This is phenomenon 4, and I'll just mention something. In fact, let me just import this file, add image, and this is phenomenon 4. This is the one I'll be probably focusing on my next lecture. So let me just put it right here. I'll just read it for you to get you set up, and then I'll talk about this more next time. Phenomenon 4. He says that the fixed stars being at rest, the periodic times of the 5 primary planets, and whether of the sun about the Earth or of the Earth about the sun, are in the sesquiplicate proportion of their mean distances from the sun. So what he's arguing here is, first of all, he mentions that we're taking the fixed stars to be at rest. So we're imagining whatever is happening within our solar system, the sun, the moon, the planets, and so on, the very distant stars, the things that we see, Orion and the Big Dipper and so on, he's taking those to be very distant and sitting still. So those are what he calls the fixed stars. They're at rest. Now, having said that, he says the times of orbit of the 5 planets are in the sesquiplicate proportion of their mean distances from the sun. So what he's doing here is he's claiming that if this is the sun here, and you look at any of the planets, you pair up any planets. So for example, if you pair up Mercury, let's use Mercury, for example, and Venus, and you measure the time of orbit of Venus. Let me go like this. If you measure the time of orbit of Venus and the time of orbit of Mercury, he says they're in the sesquiplicate ratio. There's that word again. The size of the orbit of Venus to the size of orbit of Mercury to the 3/2 power. That is what he's claiming here. He's going to present evidence, and I'll show this table next time we come around. But because any planets that you consider obey this law, which you will probably remember is Kepler's 3rd law of planetary motion, he's going to argue that this implies that there must be a force drawing them toward the sun, and that this force is a 1/r² or an inverse square kind of force law. So again, he's kind of slowly building up this argument for his universal law of gravitation, and I will stop there.